Okay. It's 2 p.m., so we can start our webinar for today. Good afternoon, everyone. Welcome to the second Green Roads webinar series for 2026. I'm Ritu Mishra, Transport Specialist with ADB, and I'll be moderating today's session. Before we begin, a couple of quick housekeeping notes. The session will last about 1 hour. All participants are welcome to submit questions through the Q&A or chat box, and we will address them during the discussions or at the end of the presentation. Or, you can raise your hand and we will hand over the floor to you for the questions. We have some interesting sessions coming up covering topics such as country-level climate hazard risk modeling, smart infrastructure, and climate-resilient road design and maintenance manuals. So please keep an eye out for those invites in the coming weeks. But today, we turn our attention to a topic with wide relevance across many contexts, which is making low-cost granular roads more resilient. Low-cost granular roads form the backbone of many rural road networks across Asia and the Pacific, as we all know. And in fact, they account for about 35% of roads globally. However, these roads are often very vulnerable to heavy rainfall, flooding, and poor material performance, which can lead to problems such as deformation, erosion, and even washouts. So in today's Green Roads webinar series, we will be exploring practical lessons from Australia, including mechanical and chemical stabilization techniques, the use of recycled materials, and emerging permeable pavement concepts that can help improve the resilience of these roads. So please stay with us until the end of this session, and we look at more practical and cost-effective solutions for building longer-lasting climate-resilient road network. And now it is my pleasure to introduce our speaker today. Our speaker today is Dr. James Grenfell from Australia. James is a principal pavement engineer leading the sustainable infrastructure materials portfolio within sustainability and materials performance at the National Transport Research Organization. James has more than 20 years of experience in pavement engineering and pavement materials, spanning both in the UK and Australia. He has researched a variety of road construction types, including bituminous binders, asphalt, concrete, unbound, granular, and stabilized materials. Since arriving at NTRO 9 years ago, his work has focused on sustainable construction techniques and the beneficial use of recycled materials in the transport infrastructure. James has published more than 100 journal papers and peer-reviewed conference papers. He sits on a number of local and international technical committees and is involved with the international research community through interaction and membership of various research associations. Welcome, James, and we're glad to have you for this presentation. And with this, I will invite Dr. James for the presentation. And after James' presentation, we'll have a Q&A session. Over to you, James. Thank you.
Thank you, Ritu. Good afternoon, everybody. I managed to share the slides right. How are we going? Thumbs up if people can see that. Perfect. Right, so I'm saying good afternoon. My name's Dr. James Grenfell. I'm a principal pavement engineer within what's now called the National Transport Research Organisation, or NTRO, formerly known as the Australian Road Research Board. And I've been given this opportunity to speak as part of the Asian Development Bank's Green Roads webinar series. So what I'm going to talk about is making low-cost granular pavements more resilient. As Ritu mentioned, there's a number of different things I'm going to touch upon, so hopefully it's an opportunity to give everybody a bit of a flavour for some of the things we've been doing. So I'll touch upon the Australian situation so that people can understand and put that in context with their own countries. I'll talk a bit about mechanical stabilization, then get into chemical stabilization, including cementitious and foam bitumen stabilization. I'll touch upon permeable and pervious pavements towards the end. And in between, there's a few bits and pieces related to recycled materials that are interwoven within the presentation. So hopefully there'll be something in it for everybody. Hopefully somebody will be able to relate to something. Hopefully there'll be some opportunities for people to take away things and maybe try things within your own region, in the hope of getting some better outcomes. Right, so to start off with, I'm going to talk a bit about the Australian situation. I don't know how well everybody knows Australia. Just to put it in, I guess, sized perspective, the land mass of Australia is around 90% of mainland USA, or the main part of USA, not including Alaska. Whereas here we've got a population of just over 25 million compared to, say, the USA with 325 million people. There's a big disparity in Australia between where people live. So there's only 5% of the population lives in the top half of the country, and around 85% of the population live in urban areas. So that means that there's a large amount of land mass with very few people living in it, which obviously presents a lot of issues in terms of building and managing a road network. And I guess the other thing that you'll notice is that most of the population is around the eastern seaboard. So Brisbane, Sydney, Canberra, Melbourne, Adelaide are all roughly around the eastern or southeastern seaboard, and that's where most of the population is. Large proportions of the centre of Australia have either no road network or nobody living in them. So again, putting things into context with the USA, and that's not necessarily very helpful for everybody that's maybe in this session, but I think most people have a bit of an appreciation for the USA in terms of what it's like. The road network in Australia is around about 900,000 kilometers, I think, these days, which is quite small in comparison to, say, the USA. The other thing is that we have a relatively small amount of the network that's actually sealed pavement. So I think some of the numbers are around 90% of the pavements in Australia are granular pavements, either with or without sprayed seal. And so only around 10% of the network is full depth bound pavements, be that asphalt or concrete. The other interesting thing is around 90% of the transport tasks are undertaken on only 20% of the network. So big disparities in terms of traffic levels as well. Here's a typical Aussie pavement with some typical Aussies, local people having a look at whether they're going for a swim or not. But typically we're talking about a thin bituminous seal on top of a granular base, which is over a granular subbase and subgrade material. I see I've managed to ruin the formatting slightly, but I should have noticed that before. And on the right-hand side is showing conveniently a typical pavement cross-section. This one actually looks like maybe it's a thin asphalt surfacing as opposed to a sprayed seal. But essentially a nice unbound granular pavement that then, due to a weather event, has essentially been washed away. So these are some of the issues that we're facing in Australia. So obviously dealing a lot with instances of very heavy rainfall, flooding events, but also Australia is a very hot country. We're subjected to extreme high temperatures, and again, that is particularly troubling for the sprayed seal network in terms of heating up binder, causing binder softening, flushing of binders, and reduction in the quality of the sprayed seal road network. And as mentioned before, certain parts of the country have very little connectivity. So, for example, there's only one major route between Adelaide and Perth. If we're to lose that direct route, you can now see that you have to drive all the way up to almost up to Darwin in the Northern Territories, across the top of WA, and all the way down through WA to get to Perth. So we're very precariously balanced in terms of the risks of losing connectivity and what that means to our road network. And again, obviously, we're affected by weather cycles, and in Australia, that we go through this continual sort of cycle between El Niño and La Niña, where we have much drier, hotter periods and much wetter periods that we obviously have to deal with in our network. And so these weather periods are typically lasting somewhere in the region of say 5 to 10 years, where we'll have 5 or 10 years of very dry period, followed by 5 or 10 years of very wet period. And obviously that's going to have significant effects on the road network and the operation of the road network. Obviously, the higher temperatures affecting bituminous surfacings, asphalt, etc., very wet conditions, really affecting the unbound granular materials below, and especially the unsealed road network. And again, obviously, as mentioned before, generally Australia is very hot. And again, mean temperatures are only obviously rising over time, significantly higher in the last 30 or 40 years, where average temperatures are continuing to go up, and understanding how to manage a network under those conditions is obviously a continuing problem. Right, the first main topic area I'm going to talk about is mechanical stabilization, or essentially how we can get the best out of our granular materials. And some of this is sort of come off the back of a number of guidance documents that we've produced over the years. One of them being a course that we've run probably for the last, 30, 40 years, which is Best Practice Guide to Unsealed Road Network. And as I mentioned, there's probably still 50 to 60% of the Australian road network is unsealed granular pavement. So it has no sprayed seal, no asphalt surfacing, nothing protecting the granular network. The granular materials. And those materials can then be very susceptible to changes in climate conditions. Obviously, in very dry conditions, they become dusty. They could be subject to loss of material, or depending again on the materials in question, may be subject to corrugations. But obviously, again, then if we get very wet conditions, we can have issues with potholing, with rutting. The unbound granular materials can become quite unstable under changes in moisture conditions. So these are some of the things, some of the problems that we have to deal with on the unsealed road network. I'm not going to go through and tell everybody about unsealed roads or how to manage them, but this document, the Unsealed Roads Best Practice Guide, is free to download through the NTRO website. Contains a lot of information to support people in terms of asset management, design, construction, and operations, etc., and is supported by a number of appendices. And some of the things I'm going to be talking about is understanding how we can get the best performance out of the unbound granular road network. I don't know how much people love graphs. Hopefully most of us are engineers, and we like to see plenty of graphs in the afternoon, especially after lunch. This is just a a relatively simple particle size distribution graph showing the typical types of materials that we might be using in our unbound road network. So we've got particle size on the x-axis, percentage passing on the y-axis, and essentially we get this, and we can analyze the materials we're using on our road network by sieving the materials through a series of ever-decreasing sieve sizes to build up an indication of the gradation of the materials that we're dealing with. So at this end, we've got coarser materials, so at the top end, we're talking about materials that's around about, I don't know, 25, 30 millimeters in size. And all the way down, once we're getting down at this end, we're talking about very fine materials. And there's a general rule of thumb at the bottom of this picture showing that we've got sort of gravelly type materials at the larger particle size moving through coarse sands to fine sands down to silts, and at the very small particle sizes, sort of the passing 75 micron, etc., the clay type materials. And typical road materials are made up of a gradation of different particle sizes, and the red line is showing a typical sort of grading envelope that we might be operating in for unbound granular materials. As we go on the coarser side, so moving to the bottom right of the graph, we get more coarse materials, so they will be working better under heavier loads. And as we move up towards the top left, we have finer gradations, so tending to be better for under lighter traffic conditions, or in wearing course conditions where we can get a tighter wearing course, a smoother surface to allow our vehicles to run on. All of this, I guess, is just kind of setting the scene of what we're trying to do. And generally, if we were looking at road building materials, we'd be aiming to be somewhere in the middle of our grading envelope to get the desired performance. And obviously, depending on whether we were talking about a base course or a heavy traffic wearing course or a light traffic wearing course, we could be at different levels within our grading envelope. Introduce you to another exciting graph now. And this graph, I think, was actually developed, or this system was developed in South Africa, but it's essentially giving us a bit of an indication of how granular materials might perform on unsealed road networks when they're used in wearing course applications. And so this time we have a graph, and it's got what's called grading coefficient on the x-axis, shrinkage product on the y-axis, where our shrinkage product is essentially a number that's the the linear shrinkage multiplied by the percentage of material passing the 0.425 millimeter sieve, or as an estimate, the plasticity index times 2.5, which will give us a good indication of the linear shrinkage, again multiplied by that passing 4.25 sieve. So that's going to give us the number on the y-axis, and our gradings coefficient, which is essentially an exciting equation made up of different amounts passing different sieve sizes. So percentage passing the 26.5 millimeter sieve minus the percentage passing the 2 millimeter sieve, all multiplied by the percentage passing the 4.75 millimeter sieve divided by 100, which will give us a gradings coefficient. So what does that mean? If we divide that chart up into quadrants, we know that unbound granular materials are tending to perform quite well if we can make them fit within this good area on the graph. If they are higher on the gradings coefficient side, they're potentially at risk of raveling. If they're low on the gradings coefficient side, they're at the risk of being erodible. If the materials are higher on the shrinkage product side, they're likely to be at risk of being slippery. If they're low on the shrinkage product side, they're likely to corrugate and ravel. So this chart now gives us an extra way to try and define how our materials might be performing in the field. So this piece of work was just undertaken to help a local shire council in Australia understand whether they could get better performance out of their available crushed rock sources to improve the longevity of their unsealed road network. And so this particular council had 4 different sourced crushed rock sources. And this graph is now showing the gradations of those different crushed rocks plotted out with a typical or the kind of the requirements or advice for the gradings envelope also shown. So you can see that some of them, the green line seems to be quite on the fine side. The blue and the purple are quite coarse in certain areas, and only really the red one is performing or sitting fairly close or closer to the middle of the grading envelope. So automatically, maybe that might start to make you think, oh, some of these materials have got some gradings deficiencies, and they might then be at risk of poor performance as far as that other chart that I showed. So unsurprisingly, we then took those or characterized those different materials, plotted out the results onto the chart, and you can see, as expected, they sit in different areas of the chart in terms of their expected performance. So actually, this green one we'd expect to perform well. Actually, looking at whether those lines are slightly different colors, aren't they? So the B material is actually the one that performs the best, sits within the good area. And then the other 3 are all potentially at risk of corrugating or raveling when used in the field. So straight away, that leads us to understand, okay, so of their 4 available materials, one of them is likely to perform well. The other 3 potentially are going to be at risk of corrugations and raveling and potentially aren't going to perform very well at all. What opportunities is this going to give us as to whether we can improve the properties of some of these poorer materials by blending with the good material? And straight away you'd think, oh, these 2, they're not that far outside the good zone. There's probably a good chance we can blend them to bring them up into good performance. Potentially we might have to try a bit harder with this 20 mil crushed rock down here, but there's definitely an opportunity to blend with proportions of this green material to bring it up into the good area. Not going to touch on this too much, but essentially this is just a bit of a table characterizing the different materials in terms of their OMC, maximum dry density, shrinkage product, gradings coefficient, etc. Looking at their soaked and unsoaked CBR. What could we do in terms of improving the gradations? So again, this is now looking at some of those materials and blending them to improve their gradation and getting them to fit much better within the grading envelope. And what does that now mean in terms of where they sit on the performance chart? So by undertaking this blending, so blending, say, 50% A with 50% B, 45% C with 55% B, and 45% D with 55% B, we've now been able to bring all of the materials up into the good area within the chart. And again, just kind of checking that from a what that might mean in terms of their performance. It's now giving us a bit of an understanding that we're able to improve how they're likely to perform. This study, it kind of stops at the desktop stage. There's the next step that we would have liked to take with that, which I'm just going to show you as part of a different project. So again, this time, this was actually working with another local government entity within Australia. In this case, they had a problem recycled crushed concrete material, so a recycled material. They also, within that council at the time, had a problem with waste glass. And therefore, we were trying to look at whether or not we could optimize the performance of the recycled crushed concrete through blending with recycled crushed glass. So this is the crushed concrete material. It was quite dry and bony. There were some quite large particles within it. It was what was called a dense graded base or dense graded subbase material with 20 millimeter aggregate size under New South Wales terminologies. The material was actually, you could physically see that there were some deficiencies in the grading. So it had some quite large particles and some gaps within the particle sizes in between. The other issue is in the last, I don't know, number of years, we've had a lot of issues with waste materials being generated and stockpiled. There was a ban put in place on us exporting our waste to other countries, which is very sensible, but that led to stockpiling and people not knowing how to process the materials to find a end use for them. And so recycled or crushed waste glass was seen as a problem. There was an opportunity to look at the processing of the waste glass and see whether or not we could use it as a viable product within road construction, and especially for improving the performance of some of the granular materials. So in this case, again, a gradings curve, the 100% crushed concrete, you can see has quite a poor gradation, is quite coarse, set at the bottom end of our grading envelope. But by blending with either 30% recycled crushed glass or 40% recycled crushed glass, we can now improve its gradation and get it to sit better within the grading envelope, which obviously then means that there's an opportunity for improved performance. So the potential to get better compaction and through improvements in gradation, and as a function of improved compaction, then improved performance. We have a device here in the laboratory at NTRO, which we call OSTRAC, or the extra large wheel tracking device. Basically, we can make up slabs of material that are 700 meters long, 500 meters wide, up to 300 millimeters deep. We compact in 50 millimeter layers, so 6 layers of 50 millimeters make up a 300 millimeter depth slab. We seal the slab with an epoxy to hold the moisture content constant, and then traffic it with a pneumatic wheel load at 8 kilonewtons for 40,000 passes to understand how it performs in the laboratory. And we've got a lot of indication of how that scales to field performance. So now a few images. So we tested the recycled crushed concrete, and straight away you can see how poorly graded this material is. Tested it under the wheel tracker. And this is an example of the 70% recycled crushed concrete, 30% crushed glass. Straight away, you should be able to see how much better the gradation, how much tighter the material is, which has obviously then led to improved performance under heavy loading. Actually, the 100% recycled crushed concrete wasn't that bad in terms of permanent deformation performance under the heavy wheel loading. The test that we undertake, we test under up to 40,000 cycles. Typically, the correlations have shown that if we can get under 14 millimeters of deformation after 40,000 passes, that the material is likely to perform well in the field in a sub-base application. So actually, although the recycled concrete didn't look that great, it probably would have performed okay in the field. But now we can see that we've blended it with recycled crushed glass and we get improved performance. And obviously there's also that additional aspect that we've now mechanically stabilized with a recycled problem material to get better performance. So you can start to see we're going to get some sustainability benefits by doing that. We then took that to a field trial. One of the things is we did see that adding even more glass actually improved the performance. We did some calculations to understand, how much available waste glass there was, and determines that probably going to 40% might be too much, and to undertake a few projects there might not be enough available recycled crushed glass after quite a small period of time. Anyway, it did lead us to doing a field trial on a section of road within Sydney. And this is just some images from the field trial construction. The job went down fairly well. People were happy with the outcome. We did some ongoing performance measurements, and everything seems to be performing very well. So this is another excellent outcome and an example of how we can use mechanical stabilization to get improved performance. So I'm not quite sure why we're moving on here. But essentially we managed to scale up the blend. So the mechanical stabilization took place essentially running the materials through a pug mill and an asphalt plant, essentially just blending the recycled crushed concrete with the recycled crushed glass at the right moisture content, delivered to site and compacted as part of this project. All right, I'm just going to touch on a few other things now. So again, there's, as I mentioned, a lot of issues with performance of granular materials. There's a lot of options to stabilize materials with a number of different products to get improved performance. And this graph just gives an indication of all the different types of stabilization techniques that are around, or different bound materials. So unbound granular materials will be down here. So we've got essentially increased permanent deformation resistance or reduced flexibility on the y-axis, increased moisture resistance on the x-axis. So things like asphalts is over here. Foam bitumen stabilized, emulsion stabilized materials are over here. In this case, we're talking about lightly cemented materials that are over here. So everything has different positions on the graph. Some start to involve more bitumen, some start to involve more cementitious type binders. If we put too much stabilizers in there, it becomes uneconomic. Although we might be able to get a very highly engineered product, it starts to become economically unviable to go down that route. But this next bit of work is just outlining some work we did through Ostros to look at what are called lightly bound cemented materials. And so essentially what we're doing is stabilizing unbound granular materials with small amounts of cementitious binder. And typically what would be what's called general blend cement, so a blend of general purpose or ordinary Portland cement with fly ash. And we're trying to get a 28-day UCS strength of between 1 and 2 MPa. And if we can manage the material's performance within that range, we know it will then perform in the field much like a modified granular material or improved granular material. But it also be much more resilient to moisture damage. So we can improve its rut resistance and stiffness. We can manage how it performs in terms of not having it block or crocodile crack. So one of the things, if we started to add more cementitious binders, it becomes stiffer and it would be more susceptible to block cracking, which becomes a big maintenance issue. But at the very low levels of cement, it will not necessarily have a long bound life, but when it breaks down into a granular material, it's breaking down into a very fine diffuse cracking pattern, and that doesn't reflect any cracking issues up through either a sprayed seal or a thin asphalt surfacing that's laid over the top of it. So what we're trying to engineer against is this type of issue where we end up with block cracking. So these materials, they have a low strength, so they're not designed to inhibit fatigue cracking. And we're essentially designing them as if they have a very limited bound life, and that we're designing for them essentially acting in a modified granular material state throughout their lifetime. And as part of this work, it was to develop a lightly bound cemented design methodology. And a lot of the work was undertaken to try and characterize the materials and help us determine a design modulus at which these materials could be worked with in real pavement scenarios. And another aspect to this was to try and understand how and where these materials have performed well and where they perform badly in the field, to understand any guidance around how they should be used in the field. So we looked at a number of different field sections in Queensland, looked at their long-term performance, and were able to correlate where they'd performed well and where they performed badly, and which helped to produce some advice around the amount of unbound granular subbase support they should require to perform well. So you can see on this graph that the materials that have performed well, they tended to have a lot of unbound granular subbase support, whereas up here, where we've got a section that's performed badly in terms of the percentage cracking over its lifetime, was seen to have very minimal subbase support over a low CBR subgrade. We tried to mimic the behavior in the laboratory, again using the extra large wheel tracking device, so that we could understand a bit more about its characteristics and how it would perform, or that shift between laboratory performance and field performance. So again, you can see that under a traffic loading, it starts to break down almost into a granular material. This is looking at the slab afterwards. So they after testing, it doesn't seemingly really break down into block cracks, but under the wheel path, the material's broken down into an unbound granular material. And again, obviously, we looked at a number of,
you have
another
less than
5 minutes or so.
Yeah. Thank you.
So we also looked at some field trial sites to help support the performance, to help us determine a presumptive modulus that could then be used in pavement design, and to come up with pavement design advice for designing with lightly bound cemented materials. So this now feeds into the Austroads Guide to Pavement Technology Part 2, which is the design of pavements. there is some rules around minimum layer thickness and minimum support for that layer based off this research in terms of granular subbase material, and also some advice around selecting presumptive moduli for the lightly bound cemented layers within pavement design, which has now led to a design method with the potential to get some thickness reductions within field construction, which is now being utilised within Queensland Department of Transport and Main Roads, and they're actually working towards publishing an update of their own methodologies to produce a pavement design supplement to incorporate this design method into their standard practice. Should probably say we're also looking at further widening some of this research to look at the option of taking some of the blending of recycled materials to be used as host materials for these stabilization techniques. And we're also working with Transport and Main Roads to look at broadening the understanding of how stabilization techniques work with different recycled host materials, so that we can adjust host materials characteristics to get better long-term performance. So not just in their unbound state, but also if we cement stabilize, or now the next one, foam bitumen stabilize. I don't know how much people know about foam bitumen stabilization, so it's a slightly different technique whereby you're foaming bitumen and also blending in a secondary binder to make a material that looks almost like a hybrid between a concrete and an asphalt. And so it's stiffer generally than asphalt materials, but also has some flexibility due to the bitumen content that gives it improved fatigue performance over cementitious or concrete materials. So we undertook a lot of work with Ostros to develop guidance and help understand the design and performance of foam bitumen stabilized pavements. And there was a lot of work that was undertaken under our accelerated loading facility to look at the permanent deformation performance and fatigue performance of these materials under accelerated loading. So this time we're talking about this bluish area, bitumen stabilized materials. So foam and emulsion sit in this part. We're adding small amounts of bitumen and cementitious, or in this case, hydrated lime, to granular materials to improve their performance in terms of moisture resistance and also reducing their susceptibility to permanent deformation. So what we're typically doing is passing water through hot bitumen, which foams up the volume by maybe 20 or 30 times for a relatively short period of time. But during that time, the materials are mixed together and the foam bitumen coats fairly well with cold granular in situ host materials, forming lots of little spot welds. We're also adding in a secondary binder, typically in Australia, hydrated lime. The materials are compacted at somewhere between 70 and 85% of optimum moisture content, and they will continue to cure with time to form a very stiff, moisture resilient and also permanent deformation resilient pavement structure. And again, these types of materials are being used quite widely in Queensland, where they've had a lot of flooding events. And here's a nice example of a foam bitumen stabilized pavement underwater. And this was a few days after the water had receded. The foam bitumen pavement was working very well. Unfortunately, the traffic lights weren't working quite so well afterwards. So as I said, typically we're adding in hydrated lime in one pass. We have a stabilizing machine or pulverizer to blend the materials together. Second pass with the bitumen, so the bitumen connects up to the pulverizer. The bitumen is foamed in the foaming rig, or water's passed through. That's then mixed in the mixing chamber. The materials are then compacted with the heavy roller to form our foam bitumen stabilized pavement, and then we would seal with either a sprayed seal or a thin asphalt surfacing. This is the ALF device. Not going to touch on that too much, but essentially we can apply simulative heavy traffic loading to full depth, full scale constructed pavements in much more controlled conditions to allow us to make a lot of good understanding in terms of how these materials are going to perform under either deformation conditions or fatigue conditions, which then allows us to improve pavement design guidance. So one thing of note, these materials perform very well in terms of deformation performance. So the red line at the top is a typical asphalt, and the foam bitumen stabilized materials with 0% wrap at the bottom, 50% wrap but a lower temperature, but then very similar temperatures. So this black line has got 50% reclaimed asphalt pavement within the host materials, foam bitumen stabilized, tested at 43 degrees C, still performing significantly better in terms of permanent deformation than the asphalt that's been tested at a slightly lower temperature under the same loading. There was quite a lot of complex testing to try and understand the fatigue performance of these materials, because there's lots of different things going on at the same time. So over time, the materials continue to cure, so they'll get stiffer with time. As you traffic them, you get a reduction in their modulus. This is just a schematic showing what was happening during the ALF pavement testing. We had to increase the load as we didn't get much damage to begin with. And then some further analysis. So this time showing that a blend of host material and wrap material performed very well in terms of fatigue. So over a significant number of wheel passes, we got a very like a 30% drop in, say, fatigue per life. In the case of an 80% cement treated material, slightly worse performance, but still these materials are performing quite well in fatigue as well as performing well in permanent deformation. So again, foam bitumen stabilization, a very good cost-effective treatment to provide flood resilience and permanent deformation resilience for granular pavements. Right, I've got a couple more slides and then we can go on to some questions. This one was more of a curiosity. We started to look at permeable and pervious pavements quite a lot for the New Zealand Transport Agency. Obviously, these types of things are what we're seeing all over the world these days, significant flooding events. How can we design our pavement structure to cope with these types of flooding events, but also potentially take advantage of this water that we can collect? So obviously a lot of the focus in this type of research has been for urban areas, but we wanted to understand whether we can find solutions for rural or even mountainous environments, or say rural, low-lying or mountainous regions. So I'm not going to talk about the urban areas, but just a few curiosities about what we discovered for that could potentially be trialed for mountainous regions or low-lying regions. So these are some schematics that we would like to take further and either undertake characterize in the laboratory and see whether or not we could design some of these things in the field. So a typical granular pavement in a mountainous area, obviously we're talking on, say, the side of a hill or the side of a mountain. We might be having significant water runoff during heavy rain events, which could essentially totally inundate pavement structure and lead to washouts. Could we build a pavement structure with that's horizontally permeable to allow water to pass through the subbase material and out to the side of the pavement without causing the washout? So these are some of the theoretical structures that we would like to take to the next level of research. So obviously opportunities, if we had systems with potentially single-size pervious subbase materials, it would allow us to get water to run under the pavement structure without actually destroying the pavement structure. And again, in a similar state in low-lying regions, if we can raise the pavement up a bit with horizontally pervious subbase materials, there's the opportunity to allow water to pass from one side of the road pavement to the other without causing significant washouts. So it's kind of looking at the kind of the final steps as to what could we do to improve the performance of unbound granular materials to make them more resilient to extreme weather events. So far, we've not managed to secure any further funding to look at this anymore in the laboratory or even lead us to field trials, but this is hopefully something that we'll be able to do in the future. So just a few concluding remarks. Obviously, there's a lot of different solutions that exist to provide improved performance and resilience of low-cost granular roads, starting with appropriate material selection, opportunities for blending and mechanical stabilization through looking at the different materials that are available to us. There's options for chemical stabilization, touched upon a couple, cementitious stabilization, foam bitumen stabilization, but there's still obviously further work to be done to see whether we can design our granular pavements to be more resilient. I've probably taken a little bit long, but we've made it to the end. And if anybody's got any questions, I'm quite happy to take them.
Well, thank you, James. It was very insightful presentation, and it's very good to see different several approaches in improving the resilience of low-cost granular roads. And as a starting point, as our audience are still tapping in the questions, I'll ask you a quick question. So, from a life cycle cost perspective, how do stabilized granular pavements compare with traditional sealed roads in terms of maintenance frequency and total cost of ownership? So I mean, you had several slides around this, but if you can quickly summarize it, and it's a very common running in everyone's mind.
Certainly, I think that's an excellent question. Obviously, the maintenance and life cycle costs are slightly different between stabilized pavements and, say, full depth bound pavements. For starters, the upfront costs are significantly less for stabilized pavements compared to full depth asphalt, for example. Whereas I think the general feeling is that some of the foam bitumen stabilized pavements, for example, could be lasting, in some cases, at least as long as the asphalt equivalents. So straight away, that's a big opportunity to save on whole of life costings. The cementitious stabilized pavements, again, even lower costs, but we need to understand where they're appropriate for use. But I think there's opportunities, obviously, to make savings over repeated rehabilitation with granular materials because we don't need to go back and maintain as often. But obviously, then it's the balance between we don't necessarily have the money to build full depth bound pavements across large parts of Australia. And therefore we can make significant construction cost savings. As for whole of life costings, I wouldn't like to hazard a guess, but I guess the general feeling is that these will have a lower whole of life maintenance costs throughout their lifetime if they're managed well.
Yep. Okay. Well, thanks, James. So we have one question from Philip. Will you investigate the performance of permeable pavement relative to sealing of voids by foreign material to inform maintenance regimes?
Yeah, obviously that's something that needs to be looked at further because there's a lot of work in, say, the urban space and what happens when porous materials start to clog and how you can maintain them to maintain their functionality. Obviously, trying to understand what that might mean for a horizontally permeable pavement. We've only got as far as sort of the theoretical aspect of it, and it's one of the aspects is how could you manage the clogging? How could you get the best performance out of your materials in terms of, say, gradation to prevent clogging from happening? So we haven't got any further in that because we haven't really got into any practical aspect, but that's one of the things that obviously needs to be looked at, and how could we manage that?
Well, thank you. We do not have any questions in the, okay, yeah, okay, one question. Okay, we have one question from Irina. First of all, say thanks for an insightful and interesting presentation. And the question is, of all the methods, which one, in your opinion, is the most ready for future climate challenges?
Well, obviously, I think all of the ones that I present, or the mechanical stabilization and the cement stabilization and foam bitumen stabilization, that they're all being implemented. And so they're all kind of off-the-shelf solutions. I think with all kind of stabilization techniques, you really need to understand your materials and try to characterize them well so that you can understand how they're likely to perform in the field. I think it's more that there's almost like a difference in a step in change in, say, costs involved in the different solutions. So the foam bitumen stabilization will be the most expensive, more appropriate to heavy traffic situations or more extreme conditions. The mechanical stabilization will be much more appropriate to situations where you might have had unsealed granular pavements. So it's understanding what type of performance you want to get out of your road network, and these are essentially solutions that could be used instead of just having either unbound granular pavements or having to take that expensive step of a full depth bound pavement, especially when you've got, say, a very long network, that it would be uneconomical to spend a lot of money with the full depth bound options.
Okay. Well, thanks, James. Maybe while waiting for another question, a quick question, which is something relating to, I would say, policies. Your presentation highlighted the use of several recycled materials, right? In practice, what institutional or regulatory barriers do road agencies typically face when scaling up these new innovations in the construction industry?
Yeah, exactly. That's obviously a complication. In Australia, what we've when we've been looking at innovative or alternative recycled materials, we've always tried to follow certain pathways or pillars. So the first thing is we're always looking to achieve at least equivalent, if not better, performance from an operational perspective. But we want to make sure that we're not using anything that's going to cause a worker health and safety or human health risk. And we want to be using technologies or solutions that there's no risk of long-term environmental harm. So we don't want to be introducing things like the potential for microplastic release or harmful leachates that could get out to the environment. And also the last thing is anything that we do, we want to make sure it's fully recyclable at end of life. So a lot of the projects we've been following through EPA guidance through different states to understand all the different stepping stones that we cover the environmental and human health aspects of everything that we do. to make sure that we're not causing any issues by introducing any new technologies. And potentially a lot of that could be around, say, the use of various recycled materials and checking that as a functioning incorporating them, we're not going to introduce harmful leachates, etc., into water courses. So all of these things, they obviously need to be checked. There's a lot of work that goes on, say, looking at industrial byproducts as part of the as supplementary cementitious materials. And again, we're always looking at whether by changing away from traditional materials like hydrated lime or cement, whether there's any risk of causing any longer term environmental harm, or whether there's any operational worker health and safety issues with implementing these materials. So there's some general guidance, and again, even through, say, Osroad's Guide to Pavement Technology Part 4E, but in terms of a framework to look at novel and recycled materials and how they should be implemented safely into transport infrastructure.
Okay. Well, thank you, James. We have already exceeded our allocated time, but we'll take last question and we'll end the session. So we have last question from Mikhail. What kind of stress testings have you conducted to ensure reliability of these solutions? We don't want to keep maintaining them once in a while.
Exactly. And again, like most of these different technologies, there's a lot of mixed design, laboratory mixed design guidance and rules around determining whether or not they're going to meet long-term performance. And so a lot of these technologies have that strong understanding that if you can do a mixed design on your particular host material with your particular stabilization solution, what minimum requirements you're looking for to get performance in the field. That's obviously then being backed up through a lot of laboratory testing, but then obviously scale up and testing either under accelerated loading to simulate long-term heavy traffic loading, or even field trial performance to understand how these materials or solutions are likely to perform in the field. So everything is kind of evidence-based, and we've got a lot of information about how well these solutions are likely to or will perform in the field. Obviously, there's still further investigations going on in terms of, what happens when you stabilize recycled host materials, for example, and how they're likely to perform. That's ongoing research that we're undertaking, especially with Transport Main Roads in Queensland, to really understand the long-term performance of some of these materials with a view to widening the implementation of some of these technologies.
Well, thanks. Before we close, I just saw one question. Maybe you can quickly respond and we'll no longer take any questions. But the question is from Soros. Can you share your experience regarding road safety in the Himalaya region? So
probably limited personally. Obviously, all of these technologies, they need to be, you would go through the same geometric design rules and guidance when you're implementing to make solutions as safe as possible. And obviously, there's a lot of safety guidance as to how you build new constructions, etc., and maintain. But all of the solutions that I've presented are they're essentially relatively standard pavement construction types, especially in Australia, that you would just implement with standard safety guidance as the same as a conventional road. So it's essentially kind of you follow the standard practice and follow business as usual to make things as safe as possible. Again, like there's safety surface treatments that you might consider, but that would be much the same as treatments that you would put on any other road. And for the stabilized materials we're talking about, they're the base materials, and you would put some kind of appropriate surfacing for the safety conditions that you require.
Well, thank you, James. I think we are good. We are we have already exceeded 4 minutes, so we'll close the session. But I would like to thank you for the very interesting and very relevant presentation. And also we'd like to thank all our attendees joining today. And we hope you found the discussion on this very useful and inspiring. And as mentioned earlier, stay tuned for upcoming sessions on country-level climate hazard risk modeling, smart infrastructure, and climate resilient road design and maintenance manuals. And yeah, I mean, and I think a link has been shared with you for your evaluation. Please fill out those links as well. And as mentioned in the chat box, the recording of this webinar will be uploaded in the website. Please feel free to go and revisit them. And with this, we would like to thank you and end this session. Have a good rest of the day. Thank you.